Bismillahirrahmanirrahim. Today we would be briefly discussing the coordinate systems, and then we would discuss the stress strain curve or stress strain plot for a ductile material and brittle material, and at the end a brief discussion about the assignment, etc. So there are a number of coordinate systems which we normally used in engineering and sciences, but the most popular one are actually the Cartesian coordinate system, spherical coordinate system, and cylindrical coordinate system. In Cartesian coordinate system, we have three axes, which are x-axis, y-axis, and z-axis. And any point in space is denoted by the coordinates x, y, and z. X is this distance, which is along x-axis, y is the distance along y-axis, and similarly z is the distance along z-axis. In spherical coordinates, we use the coordinates r, theta, and phi. And any point in space would have these coordinates r. R is the distance of the point from the origin. This is r. Theta is the angle which this line is making with z-axis, and phi is the angle which the projection of this line. If we draw the projection of this line on xy plane, then this would be the projection of line r, and the angle which the projection of this line is making with x-axis is actually phi. So here we have the coordinates r, theta, and phi for a point in space. Also, in cylindrical coordinate system, we have the coordinates r, theta, and h or z. Sometimes we write h, or sometimes in some books you would see z. So here any point in space would have these coordinates r, theta, and z. R, theta, and z. R is the distance of the point, if I draw the projection of this point on the xy plane, this is the xy plane, the projection of this point would be here. So the distance of the projection of the point and the origin is r, and the angle which this line r is making with x-axis, it is theta, and z is the distance of the point from the xy plane. So here we would have the coordinates r, theta, and z. So actually all coordinate systems which we have or which we are using in engineering and sciences are good and correct. The choice of selection of a coordinate system completely depends upon us. And normally we have to choose the coordinate system in such a way that actually when we are doing the modeling or mathematics for the problem, then it should be easy in that specific coordinate system. And also the equations which we got in the coordinate system or while solving the problems, those equations need to be simple so that we could solve the problem easy and in less time. So the choice of coordinate system is completely upon us, but we have to think cleverly, and we depending upon the shape, depending upon the shape of the system, we have to select such a coordinate system in which our work is easy, which make our life easy. For example, if we want to analyze something inside a room, so if we look at the room is just like a cuboid, or it is a cube. So normally, if we think that which coordinate system we have to use, so very easily we could we could select, or we could see that actually the Cartesian coordinate system would be good while working in the shape like cuboids, cube. So for room, we have to select a Cartesian coordinate. Similarly, if we are working or analyzing the globe or earth or any spherical shape like a ball, so actually it is better to select the spherical coordinate system. So for such system, the spherical coordinate, working in the spherical coordinate system would be easy. The modeling would be easy. The mathematical equations that we would get there, those would be easy. The solution of those mathematical equations would be easy. Similarly, if we have a cylindrical system, then our choice would be the cylindrical coordinate. For example, if we have a shaft and the shaft is actually of the cylindrical shape, so it is better to use the cylindrical coordinates for the analysis of shaft, etc. So actually, during this course, depending upon specific problem, shape of the mechanical component, for our ease, we have to select the proper coordinate system. So sometimes we would select Cartesian coordinate system, sometimes spherical coordinate system, or sometimes cylindrical coordinate system. Some more discussion about stress and strain. Last time we had discussed that stress and strain are actually tensors, and normally we have to define stress and strain at a point inside the material, and it would have 9 components. So normally we define the stress at 3 mutual perpendicular planes. As you see here, this is the Cartesian coordinates, and we define the stress at 3 mutually perpendicular planes, and we would have all these 9 components. For stress, here we would have these. This is the stress tensor, and it would have 9 components, and these components are actually defined at 3 mutually perpendicular planes. And what are those 3 mutual perpendicular planes? XY plane, ZY plane, and XZ plane. So these have been defined on these 3 mutual perpendicular planes, or in this coordinate frame X, Y, Z. Similarly, this is the strain tensor, um, and again it is a tensor, and it would have 9 components, and the terminology is the same. The first subscript represents the direction of the normal of the face or normal of the area, and the second subscript represents the direction of the force. And again, they have been defined in a Cartesian coordinate system. Um, we also discussed that stress and strain is such a concept that if we change the orientation of the coordinate frame, then the values of the stress would change, these values would change, and also the values of the strain would change. For example, uh, if the orientation of the frame is this, the gray line, and if we keep the origin fixed, so about this origin, if we rotate the frame, so and if we think about the different positions with respect to the x prime, y prime, and z prime frame, with respect to that, we would have infinite number of positions. It means that we would have infinite number of frames at point O dash, at point O dash. What does that mean? It means that we would have infinite number of different values for the stress and strain. All would be correct. All would be correct. It the choice of a specific frame or orientation of frame completely depends upon us, and we have to choose sometimes the frame just like this, or sometimes we would rotate the frame and we would do the calculation why we are rotating the frame. All we would study in this course, and you would learn that what would be the benefit of doing that. So remember that there would be infinite number of coordinate frames in which we could define the stress and strain. But there is one specific frame. In those all infinite number of frames, coordinate frames, there would be one specific frame where what would happen, all these shear components would become zero, and we would have only values along the diagonal. We would have only values for the normal stress. So we would have only values for the normal strains here and normal stresses here, and all the remaining values, that is shear stress, would disappear, and here we would have zero. This matrix would turn like this. We would have only values along the diagonal. We have only values for the normal stress. The all shear stress component would be zero. So that particular uh, frame, coordinate frame, is known as principal frame, and the corresponding axes in that frame, they are known as principal axes, and the corresponding normal stresses are known as principal stresses. And in these principal stresses, some would be maximum, one or two would be maximum, and that would be the maximum stress at that point in the material based on that coordinate frame. Similarly, here in the at the principal axes, or in the principal planes, principal coordinate frame, the strain tensor or matrix would have only components along the diagonal, along the principal axes, and the values, the shear strain values would be all zero. So actually, normally when working with the stress and strains, it is very, very important that we should know the orientation of the principal axes, or we should know the principal coordinate frame, and we should also know the principal stresses and principal strains. So that is very important. So when we are solving, or when we are analyzing, or when we are working with stress, so it is very, very important that we should know the principal strains, because as I told you that in the principal stress would be the maximum stress. So normally when we are designing the mechanical components, so eh, for the we have to design for the maximum stress. So we should know that maximum stress. Also, we should know the orientation of the principal planes, because in that case, before the failure in hand, we would have the prediction that if the failure would occur, it would occur at that particular plane, or at that particular axis, because at that axis, or at those axes, the stress is maximum. So the material will fail along those lines, along those axes where the stress is maximum. So we need to find that maximum stress. We need to find the orientation of that particular axis or axis. So um, there will be only one coordinate frame where all shear components would be zero. Remember, only one coordinate frame where all shear components would be zero. that coordinate frame is principal coordinate frame, and the axes would be principal axes, and the stresses, the normal stresses would be principal stresses. So in that case normally sigma xx is denoted by sigma 1 1, or sigma 1. Sigma yy is denoted by sigma 2 2, or for simplicity sigma 2, or sigma zz is represented by sigma 3 3, or sigma 3. 1 2 3 are actually the principal axes. These are the notations that we normally use for principal axes 1 2 and 3. So just go back what we have discussed in our previous lecture. In the previous lecture, we discussed that if we have a rod and we are subjecting the rod to a tensile loading, and we take a point Q inside the material, and if we calculate the stress, the value of the stress depends upon the orientation of the cutting plane or orientation of the frame. Let's say if we have x, if we are taking x, y and z frame at point Q, then what would be the answer? We would have only one normal stress, and that would be sigma yy, and all of the remaining stresses uh, would be zero. And in that case, the stress matrix would be this one. So here, if you look at the stress matrix, so all the shear components are zero. So what does that mean? It means that the particular, in this particular case, the coordinate frame x, y, and z is which type of frame? It is the principal coordinate frame. And in this particular case, x, y, and z, they are principal axes. They are principal axes. Here, this normal stress is zero because there is no loading here. And also this normal stress is zero because there is no loading along z-axis. There is no loading along x-axis. We have only loading along y-axis. That's why we have sigma yy. And this sigma yy is the principal stress. It is the principal stress. So conclusion is that the coordinate frame x, y, and z in this particular case is a principal coordinate frame. And if we change the orientation about point Q, if we change the orientation of the coordinate frame and we rotate this coordinate frame and make it x prime, y prime, and z prime, then we already discussed that in that case the shear stress would appear. So in that case we would have two stresses here, sigma y prime, sigma y prime, and tau x prime y prime. And we know that the cross shears are always equal. So here it means that tau y prime x prime would be also there. So if we look at this stress matrix, so here you could see that all of the shear components are not zero. What does that mean? It means that the x prime, y prime, and z prime is not the principal coordinate frame, or these are not the principal axes, and these are not the principal stresses. Remember that there would be only one principal coordinate frame, or we would have only one principal axis, one frame where we have principal axis. And in this particular case, that principal coordinate frame is x, y, and z. So we already discussed that the normal stress would be maximum at one of the principal axes or axes, and we are interested in that because normally in majority of the cases when failure would occur, The failure would occur at those planes where the normal stress is maximum. So we are interested in finding out that value and the orientation where we have that maximum stress value. Also, when we are rotating the coordinate frame about the point within the material, there would be also one particular frame where the shear stress would be maximum. So at one particular, there will be only one particular frame where the shear stress would be maximum, and the normal stresses which are along the diagonal, those would be average. We are also interested in finding out the maximum shear stress because there are materials or there are conditions, loading conditions depend upon on the loading conditions. There are cases where the material fail along the planes where shear stress is maximum. So we would discuss this in also in this course. We would see the examples where the material would have fail along the planes where shear stress would be maximum. So we are also interested in finding out the maximum shear stress, the orientation of the planes where shear stress is maximum. So in all this course, we would be interested in finding out the stress values, the principal stresses, the maximum shear stress, maximum normal stress, orientation of the principal axis, the orientation of the axis or axes where the shear stress is maximum, and all those tools we would be discussing in this course, and we would be learning all those techniques with which we would be finding all those things. So next topic that I would like to discuss with you is the stress strain curve. And for the stress strain curve, normally we do testing, and that testing is known as stress strain testing. And that testing is performed in a machine which is known as universal testing machine, simply known as UTM. So here in this slide, you could see the picture of a universal testing machine. It comprises of chucks. One chuck is here and the other chuck is here, where you could install the specimen. And normally, in majority of the cases, hydraulic system is used to move these two chucks relative to each other, and here in the chucks we have load cells or force sensor. So in the apparatus we have force sensor or load sensors, which are actually measuring the force which we are exerting on the specimen. And there is also a displacement sensor which is actually measuring the deformation that is happening inside the material. And all these sensors are connected through the hardware of the machine, and and we have a software also where a programming is done, and actually the machine gives us directly the values of the stress and strain, or it actually plots between the stress and the strain. So with the apparatus we would get the stress strain curve, which we would be discussing on the next slide. On this machine we could perform tensile testing, we could perform compressive testing, we could perform torsional testing, and we could also perform bending testing. For the compression testing, we have to put the specimen here, and we have to move this portion in the downward direction in order to compress the specimen or the test specimen, and takes the reading. Similarly, the bending experiment is also done here. And for the tensile testing, we have to put the specimen here, and these two have to move opposite to each other. Similarly, compression test could also be performed here. You could put specimen, and these two have to move close to each other. In case of torsional, we have to put the specimen, and one of these chuck have to rotate so that we subject the material or specimen to the twisting effect. Here you could see the close-up view of the chucks of the universal testing machine, and you could see the specimen. This is the specimen in between the chucks of the universal testing machine, and this is the close-up view of the test specimen. Here you could see the threads here, so we could screw the test specimen in the chuck. And here you could see the two dots, and the distance between these two dots is known as gauge length. So this is the gauge length of the specimen, and we have to enter this gauge length of the specimen in the machine. So in the computer, what we have to enter? We have to enter the diameter of the specimen, we have to enter the gauge length of the specimen. Those we have to enter. So using this gauge length and using this diameter, we would have done, there would be programming would have already be done in the software of the machine. So we have to just enter the diameter and gauge length, and when we subject the material to, let's say, tensile loading, then what would happen? The material would elongate, the length of this specimen would increase. So the displacement sensor would be recording the deformation, whereas the force sensor would be recording the force or measuring the force which we are acting on the specimen. And from the diameter, the program would calculate the area, and it would be taking the force from the sensor. So force divided by the cross-section area of the material, the program would calculate the stress. And from the deformation, which the displacement sensor is measuring, deformation divided by this original length or gauge length, the program would calculate the strain. Similarly, the program would be doing this calculation, and at the same time the program would be plotting, or the software would be plotting, the curve between the stress and strain. Remember that the machine is not measuring the stress and strain. It is measuring the force which you are exerting on the specimen and the deformation which is happening inside the material. Remember that we cannot measure stress, we can only calculate stress. Similarly, strain, we are not directly measuring the strain, we are measuring the deformation. The software would calculate the strain, or we could calculate the strain. So the machine is only measuring the force and deformation and doing the calculation and drawing the stress strain curve. So this is the stress strain curve for a ductile material such as steel or mild steel. So this is the stress strain curve for a mild steel, and along the horizontal axis we have strain, which is denoted by epsilon, and along the vertical axis we have sigma, which is the normal stress, and this is the origin O. When there is no loading, there would be no strain, no deformation. But as we start subjecting the specimen to the load, as we increase the load, so what would happen? Deformation would start occur, and we would have strain. And in that case, we would be increasing the load, and at the same time, the deformation is increasing. So we are increasing the stress is increasing, and also the strain is increasing in the material. And to a specific point, which is known as proportional limit, the stress is directly proportional to strain. Up to a proportional limit, the stress is directly proportional to strain. That's why we have this inclined line or straight line. So up to proportional limit, the stress would be directly proportional to strain. This law is known as Hooke's law. Stress is directly proportional to strain. Sigma is proportional to epsilon. And if we remove the constant of proportion, or if we remove the sign of proportionality or replace the sign of proportionality with constant, then it would be sigma is equal to E epsilon, where E is the Young's modulus or modulus of elasticity. So up to proportional limit, stress would be directly proportional to strain. Beyond that, the as we further apply the load, the stress would be no longer directly proportional to the strain. In the further, if we move, we would reach a point which is known as elastic limit. Elastic limit is also very important. Below the elastic limit, if we remove the load on the material would be capable to regain its original dimensions and it would come back here. So below elastic limit, if we unload the material would be capable to regain its original dimension. But after or beyond the elastic limit, if we cross the elastic limit, then actually permanent deformation would start happening. And so after the elastic limit, if we remove the load, the material would be not able to regain its original dimension. What does that mean? It means that permanent set or permanent deformation has actually start within the material. And if we further apply the load, we would reach a point P, and that point is known as yield point. And you could see that the line from point B to point C is completely horizontal. It is completely horizontal. What does it mean? If you look at here, the stress is constant. From point B to point C, the stress is constant. However, what is happening to the strain? Strain has increased from here to here. Considerable amount of strain has happened, or considerable amount of deformation has happened without increasing the load. It means that considerable amount of deformation has happened without increasing the applied load. So this phenomena is known as yielding. This is known as yielding. So when we reach this point, yield point, permanent deformation would start in the material, or permanent set would happen in the material, or yielding would start in the material. Without excessive load, without increasing the load, considerable amount of strain would occur. And actually the practical reason for that is that actually when we reach the yield point, at that point the planes within the material would start slipping. It would start slipping. So without increasing the load, the planes would slip and considerable amount of deformation would occur and we would reach point C. The bonds would break, the planes would slide, considerable amount of deformation would occur even at the constant load without increasing the load. We would reach point C. But when point C is reached, again the material would regain its hardness. It would regain its hardness. And again the material would start resisting the load. It would start taking the load. So here again, if we increase the load, then the strain or deformation would occur, and we would be getting this line. We would reach point D, and afterward the actually the material would be deforming. The material would start deforming. The material would become weak and it would start deforming even at lower values of load or stress. And then at a particular point, that is point E, the material would fracture or fail. So we would have this stress strain curve. So, and this stress strain curve, you would get this plot from the machine. So here, if we look to the horizontal axis, here you see a linear region. So from here to here, from point O to point A, the stress is directly proportional to strain. So stress is linearly proportional to strain. So this is a linear region. And from point E, from this point or from point B, yielding is occurring. Perfect plasticity or yielding is occurring. So this is actually yielding zone. And at point C, as the material again regain its strength and behaves harden, and this phenomena is known as strain hardening, because already considerable amount of strain has happened, and again it become started resisting the load. So from here to here we have strain hardening. And then from point D to point E we have necking. Necking is this phenomena when considerable amount of decrease in diameter happens. Because we are subjecting the material to tensile loading, we are pulling the material. So the diameter, the length of the material or the length of this specimen would increase. However, the diameter the diameter of the specimen would decrease. And once you would see the considerable decrease in the diameter, it would be visible. In the beginning it would be not visible because it would be too small, but after considerable amount of decrease in diameter happens, so you could even see the decrease in diameter, and that phenomena is known as necking. And at this point, at this position, actually the failure would occur. So even we could see the specimen that where the failure may actually take place. So here you could see that at the necking portion, the failure has occurred. And this is the fracture would occur. So we would have this stress strain curve. And corresponding to these points, we would have for stress values corresponding to point B, we would have yield stress, because at this stress yielding would occur. It is also known as yield strength. And corresponding to point D is the maximum actually stress which the material has taken. So point D is known as the ultimate stress or ultimate strength. Strength is actually the maximum stress value for a material. So we, instead of stress, we normally call it ultimate strength, yield strength. Here you could also see the dotted line. Actually, when the machine is plotting this stress strain curve, so actually it is calculating the stress, and it is calculating stress from by load per unit area. And area, it for that area it is using the diameter of the specimen, which we have initially provided in the program. We have entered this diameter, but actually we know that when we are subjecting the material to tensile loading, the diameter of the material is are actually decreasing. It is decreasing, it is not constant. This plot, the full line or dark line, is actually based on the constant diameter, constant area. But we know that when actually the deformation occurs in the material, this diameter would be not constant. So actually we are moving a little bit away from the reality. So somehow from here to here, this is just a theoretical line. In order to make it more close to the reality, what we would do, normally you will take the vernier caliper and you will pick the fail specimen, and you have to measure this diameter, the diameter at the neck. And then again you have to enter the new diameter, which would be less than the old diameter. And then again we would calculate the stress. And when we plot that stress values based on the smaller diameter, we would get this dotted line. You would get this dotted line. So this would be the true stress strain line. The dotted line is actually the true stress strain line. And here we could see that the failure would occur at this. This is actually the true fracture strength. This is actually the fracture strength based on the constant area, which is somehow not true. So we have to also draw this true stress strain curve. So what is actually important things from this stress strain curve? Number one is that actually uh, up to proportional limit, stress is directly proportional to strain. Elastic limit is also important. If your stress values are less than the elastic limit, if unload the material would regain its original dimension. Beyond that, yielding would occur. So this point is proportional limit is important. Normally during designing or during modeling, normally we could use that limit. Similarly, yield strength or point B is important because at that point the yielding would occur. Permanent deformation would occur. So once permanent deformation, sometimes people think that this is the maximum stress. We have to design the things for the ultimate stress. Ultimate stress because this is the maximum stress the material is taking, but that is not the case. If you are designing your components for this, so before that, permanent deformation would have already been occurred in your material or system, and it would be not working properly in your machine or in your system. The component is gone when the permanent deformation actually happens inside the material. So normally in engineering, we could actually design our components for the yield strength because afterward permanent deformation would occur and the component is actually of no use. For example, if we have a bicycle and in the bicycle the one of the wheel of the bicycle permanent deformation occur and it is no longer round, then if you are actually riding that bicycle, then actually the ride would be not enjoyable. Similarly, if one or two of the wheels or tires in the tires of the automobile permanent deformation has been occurred, then there would be a lot of vibrations in the vehicle which is not desirable. Similarly, if permanent deformation has happened in the working component of the machine, the performance of the machine would be not good. That component would fail after some time. Before failing, actually it would have damaged a lot of other components within the machine, which is not desirable. So one of the important point you have to note down that we have to design the components for the yield strength. On this slide, actually, you could see all of the explanation which we have discussed. So you could read all those here again. This is the stress strain curve. This is the stress strain curve for low carbon steel. All those things which we have discussed, you could find on this slide. You could also, in your books, you could see the stress strain curve for different materials, ductile materials, brittle material, um, different alloys, etc. This is the sorry. This is the stress strain curve for a brittle material. So for a brittle material, actually you are not seeing a number of points. Um, the proportional limit is not so visible. The elastic limit is not so visible. The yield point is not so visible. The stress is increasing, the strain is increasing, and suddenly we would see the rupture. This is here. This is the failure of a brittle material. The failure of the brittle material is like this. There is no necking. No necking actually happens in the brittle material. In the ductile material, this is the main differentiation between the ductile material and brittle material. If somebody shows you the specimen and you see the necking phenomena, so it very easily you could say or simply say to him that the material is a ductile material. In the ductile material, there would be a prominent necking. In the brittle material, there would be no necking, and the stress strain curve would be like this. how to find the yield point in this case, that would be the assignment. So when we have a stress strain curve like this for a brittle material, how to find out the yield point. So that would be the assignment for this lecture also. So actually, as we discussed that when we are designing the components, so one of the point that we could consider is the yield point or yield strength, because afterward permanent set would occur in the material, permanent deformation would occur in the material, and the component would be of no use. But actually that is true in case of static loading. When we have a static loading and we have a component subjecting, when we have a component and we are subjecting it to the static loading, so you have to design it based on the yield strength. In majority of the cases, when there are moving parts in the machine, we are subjecting the components, mechanical components, to the cyclic loading or repeated loadings. So normally, through experience, we come to know that in those all those repeated loading or cyclic loading, the material has actually failed well below the yield strength. And when actually scientists and engineers work on that, they come up with another um, strength value, which is known as endurance limit, which is known as endurance limit. The phenomena of failure of a material because of repeating loading or cyclic loading or alternating loading, that phenomena is known as fatigue. And in the fatigue, we come to know that the material would fail well below the yield strength. And for the cyclic loading, we have to design the material for the endurance limit. You would study all these things in your mechanical design course. And the endurance limit is actually the function of field strength. Endurance limit is actually equal to these factors Ka, Kb, Kc, Kd, etc. multiply by the yield strength. Again, we need the yield strength. So you have to, for the material, you have to perform the testing in the universal testing machine. You have to find out the yield strength, and then you have to multiply um, the yield strength with all these factors. In most of the case, these factors would be less than 1. So when you multiply all these factors with yield strength, so the value of the endurance limit would be always less than the yield strength. And these factors are shape factor, machining factor, stress concentration factor, reliability factor. All those actually explanation is present in all of the machine design books. You could go there, you could see this. But remember that we have to perform experiment and we have to find out the yield strength. Also some one paragraph is written here, you could read it, because last time a student asked question that is why the material would fail in the middle. Remember that the specimen should break ideally at the middle, but for that case the material must be homogeneous. Its composition must be homogeneous. Homogeneous material, when the material is same throughout, then it is homogeneous material. But normally in reality, normally it is there should be blowholes within the material, cracks within the material. So if that is the case, then in that case specimen, it is not be possible that the material will break just in the middle of the specimen, etc. So with this, I'm finishing the lecture. Thank you.